Hello everyone. My name is Sampada Koirala. We are here from Florida Tech, and we are here to present hydrogel radiating shielding viability under the influence of microgravity. And Caroline is here to present the slide. Thank you.
Hi, so in this presentation, I'm going to be going over some background on our experiment, our pre-flight groundwork, our experimental design, and our expected results. So for some background, radiation is simply the release of energy. Ionizing radiation is the release of very high frequency energy that's capable of removing electrons from the atoms in its path. This renders them very charged reactive particles. In the human body, ionizing radiation can cause damage to DNA by breaking covalent bonds, as well as accumulating free radicals. On Earth, humans are generally protected from ionizing radiation due to the atmosphere and magnetic field. However, in space, astronauts are left vulnerable. Figure 2 highlights or illustrates 30-day ionizing radiation exposure limits set by NASA, indicating the need for a wearable radiation protection material. Figure 3 showcases some common radiation shielding materials, but note how these materials are very heavy, bulky, and not suitable for launch or wearable daily use. Thus, the need for a wearable, flexible, lightweight material for radiation shielding during spaceflight arises. Hydrogels are known for their water retention, flexibility, and biocompatibility. Due to this high degree of water retention, hydrogels are suitable radiation shields because they can effectively and evenly protect against radiation. On Earth, hydrogels are already used as radiation shields during targeted radiation therapy, where they protect healthy tissues from ionizing radiation directed at tumors. However, in space, aggregation or clumping may occur, which would cause the hydrogel's structure to be compromised and uneven protection from radiation to occur. Thus, this leads us to our fundamental question: how will microgravity affect the radiation shielding properties of hydrogels? Regarding our pre-flight groundwork, we synthesized 11 weight percent polyvinyl alcohol, or PVA hydrogels, by dissolving PVA powder in phosphate buffered saline. You can see a detailed procedure below. So prior to flight, these hydrogels will undergo freeze-thaw cycling, which will enhance physical cross-linking and in turn enhance physical strength. So the hydrogels created on Earth will undergo baseline characterization so that after launch, we have an Earth control group to compare our microgravity exposed samples to. Our experiment will utilize all 3 volumes of the FME mini lab, with volume 1 containing polysorbate 20, volume 2 containing the dehydrated hydrogel pellet, and volume 3 containing deionized water. Our experiment won't be activated until aboard the ISS when a crew member opens clamp B, allowing deionized water to rehydrate the hydrogel. And then the experiment will be left for 12 days untouched to allow microgravity's effects to propagate. And prior to re-entry, polysorbate 20 will be released via clamp A, allowing the gel's structure formed in microgravity to be maintained and not allowing re-entry or Earth's gravity to affect the gel structure that was formed during microgravity. So essentially, we'll have our microgravity exposed sample to compare to our Earth control and have that structure maintained. Regarding our expected results, we hypothesize that aggregation will not occur due to the highly cross-linked nature of our hydrogels. But we also hypothesize that any aggregation that does occur will directly diminish the radiation shielding properties of the hydrogel. These results will be corroborated with materials characterization techniques such as dynamic light scattering, cryogenic scanning electron microscopy, and tensile testing. So we want to give a big thank you to Dr. Goldstein and the rest of the SSEP for providing us with this wonderful opportunity, as well as our university coordinators and review board, Dr. Palmer and Dr. Kiss. I also want to say thank you to our other Florida Tech teams. You guys did amazing, and I was so happy to see your presentations. And then the rest of our project team who couldn't be here today, including Layla Avant, Emily Matheson, and Leighton Carpinia. Now, we also want to thank you for listening, and Sampa, do you have any? If you want to have any questions for us.
If you guys have any questions. Thank you.
Any questions? All right, thank you guys very much.